Welcome to Calculus in the PM. Mr. Sandalki here. Now, it's a beautiful sunny day. It's 26 degrees inside this classroom. Traffic is running smoothly on College Avenue today. There is a construction zone further west, down to one lane, so be prepared and put that into your plans if you're traveling. Now, we looked the other day at the example of rates, and the specific example that we use most often is distance or position, velocity, and acceleration. And the relationship between velocity, acceleration, and distance, it's all calculus. If you have a position function, or we say distance loosely, right? A position function tells you where you are, and you do the derivative of that position function. I'll just do this right here and then I'll erase it. If we have position, and typically in math, we call that S as a function of time, typically. If you have a position function, what's the relationship between that and the velocity function? It's the derivative. So, I'm going to use this ds by dt here notation, though I like it better. So, where was I? Velocity as a function of time is just equal to the derivative of the position function with respect to time, right? Now, if you want to have a relationship between velocity and acceleration, you'll notice, by the way, some eccentricity I have. I tend to make my A's, when I'm talking about acceleration, I make my A's like a typewriter kind of A or whatever. You guys don't even know what typewriters really are, kind of. You've heard about them. Anyways, whereas other A's, I just make it like this. You don't have to make the A like this, okay? But incidentally, the relationship here is acceleration describes how fast the velocity is changing in a sense. It's the rate of change of velocity. So we could say this, dv by dt. Or, if we want to relate that to position, acceleration is the second derivative of the position function with respect to time. Okay? Now this is stuff you have in your notes, but keeping this in mind at all times. Okay? That's how they're related. Yes?
The notation for the second derivative is d squared
Oh.
d squared.
Exactly. Caught me. Good. Now, the reason why I like the ds by dt kind of notation is it's better if you are asked to come up with units. And, well, if I had time, say, measured in, let's go with seconds, and centimeters for position. So if my unit here was centimeters, what would my unit for the velocity be? Yeah, the change in S, centimeters, and then I told you the time in seconds, so centimeters per second. Right? Now, the velocity acceleration is centimeters per second every second. And that's actually a better way, and we're going to write it the other way around. But I think this is easier to understand if you think of this as centimeters per second every second instead of centimeters per second squared. However, I will always write it as centimeters per second squared. But really what this centimeters per second squared means is the velocity is changing by, if you get 2, for example. Or let's use negative 9.8, that's meters. So 980 centimeters per second squared. That means the velocity is changing by 980 centimeters per second. Every second, it's picking it up as an object falls, for example. That's what acceleration kind of describes. Now, I'm not going to get into too much physics right now, but we will actually, this will enhance your understanding of physics, for sure. Now, that's just a review of where we were at. The rest is just algebraic skills, and I didn't mean to do that there, so I'll just pin this down. Lock into place. Okay, we're ready to delete. Okay, good enough. Now here's an A, B, C, D, E, F. Oh boy, doesn't stop. Problem. I have a function, S, and a particle moves along a line so that its position at any time t greater than 0, so no negative times, is given by this function. Okay. Where S is measured in meters, t in seconds in this case. Okay. Here's my position function. And remember, this function, you might be thinking, oh, if I graph this, it will look like, it'll be a quadratic, right? But it's not that this is moving on some kind of curve. It's going back and forth and back and, you know, that kind of thing. Not multiple times. Find the displacement during the first 5 seconds. Now, physics people will remember what displacement means. Tell us, physics people. Not, because I'm hearing from you. You guys in physics? Displacement. No? Yes. Are you in physics? No. Okay. Who else? Who's in physics? Okay, just 3 of you right now? Okay, tell me displacement.
Displacement's from its original spot where it's starting. It's like how far it is from its original spot.
How is that different than distance?
Because you can like move back and forth and back and forth.
So meaning, and the stupid example is, I'm on a racetrack, I run 400 meters. That's my distance, 400 meters. My displacement is 0.
You start the distance.
Right, okay. So this is displacement. When we find our displacement, well, let's see A. The displacement during the first 5 seconds. Particle moves along the line, so its position at any time. So how do we find displacement? We have to figure out where it was at time 0 and where it is at time 5.
0 is at 2.
So the change in S, right, and you can see that 0 is at 2, but I'm going to just, you ever use delta, like the change? Okay, the Greek letter delta. That's the capital. Okay. So we're going to go final minus initial, always. The position at time 5, subtracting the position at time 0. And then you just put this into your calculator, or your head, actually. This one's able to be done. 25, so 5 squared, minus 15. 10 plus 2 is 12. Okay. Subtract 2, as you can quickly see, for 0. This is in units of meters? Yeah, this was meters. So, 10 meters. So, I don't know if it was directly from 2 to 12, because I would get the same if I went from 2 back to here, to the starting point, and back here, and then back here, and then ended up. Agreed? Like, I know because this is quadratic, it doesn't take that many back and forths. But we don't know right now with analyzing further whether it was some scenario where you go back and forth a bit or directly. You can probably tell if you know a little bit about quadratics, but the net result. Okay, so that's displacement. And this is more for the benefit of people who haven't used the word as much.
What's S's and what's Y's?
Ah. That's why I don't like using this S notation. I'll make this S look curvier. But anytime I'm plugging something in, it's a 5. S of 5 minus S of 0. Yeah, maybe a handwritten S, yeah. I should. S's and 5s are I'm sloppy, and it's hard to tell, but that's the way it is. Just keep clarifying. So B, find the average velocity, not the instantaneous, during the first 5 seconds. So if I say average, Emma's going to help me out with this, though. I think you put up your hand, right?
Yeah.
Okay, the average velocity from 0 to 5, okay? It's basically this average, it's the slope kind of.
So we check the velocity, it's near velocity of 5, and then we add 5 or 2.
No, that's exactly,
No,
that's good because, no, I'm glad you brought that up because I was going to bring that up after. So, think of it this way, and I might have brought this up before, but if you're traveling from Regina to Saskatoon, you're typically going 110. However, there's one town, the highway goes through by a valley, and is it 80 zone there or 60 even?
70.
70. Okay. So you're going 110 past Lumsden, and what is it, not Dilka? Chamberlain. You slow down for a little bit here, you're going 70 kilometers per hour, by the way. Then, for a longer amount of time, 110. If I took the average of those three numbers, you would not find an accurate average speed, would you? Because the 70 would have too much weight, too much emphasis on that, right? This is only for like maybe 5 minutes when you go through Chamberlain, right? Most of the time, your average will be like 109 or something like that. If you take the total distance over the total time, that's what you want, okay?
It's 2.
So, and this goes back to, and I'm going to just pause the video here. As Paul said, I'm talking average velocity, so it's actually total displacement over total time, which is different than distance. We already have figured out the displacement in N. 10 meters traveled in a span of 5 seconds. So, 2. And that's meters per second. Units are important, if possible. Sometimes you're given functions without units. So, I guess I should have put average velocity is really equal to the change in position over the change in time. And really, when you see change in position over change in time, doesn't that look like it's the slope formula? Y minus y over x minus x, right? That really is the slope of, if you were to graph S. It's the slope for the secant line that, or whatever the line is that from one point to the other point. That's really what you're doing, is converting that curve into a slope, a straight line drawn between the 2 points. So, ABC. C asks us, okay, you're right, instantaneous velocity. And that's what we reviewed right away. If you want instantaneous velocity, that's where you do derivatives. And we know it's the derivative of the position function for velocity. I'm going to write this out, though, because I'm instructed. Normally, I just jump straight to it. The velocity function is, I got to look at the function here. Oh, there it is. 2t minus 3. And that's with respect to time that I did the velocity, right? Now that's the function, and we want it at 4. The velocity at 4 is 2 times 4, 8, minus 3, 5. And it's meters per second. Okay? 5 meters every second. Questions? Okay. That's a 5 and not an S, and my S is in the meters per second. The number 5, the letter S for seconds. Okay. CD. Well, maybe put my D beside this one.
Can we write that as prime t?
If you wish to put S prime T, sure. But if you do, then I'm just wondering, because I don't mark final, like the AP things. If you declared right here that V is equal to S prime, then you could do S prime. you got to make it clear to whoever's marking that you know what you're talking about. That's all. I'm just worried that you might, and I don't know. I wouldn't. A, B, C, D. Why skip D? Anyways, that's why I'm hesitant to say yes for sure. I won't have a problem. But anyways, acceleration function. The derivative of this, 2t minus 3, the derivative is 2 meters per second squared. Now, the acceleration, I just did the derivative. It's the second derivative of the position.
So b squared also will be.
I'm sorry, what's that?
So, but you have to like explain that a is equal to b.
Sure. Yeah.
Used to.
I'm doing this for instruction reasons, though. So to show your work, you could skip directly into v is equal to, a is equal to. But it's actually probably wise if you're going to do that to get into that habit too. And that means 2 meters per second of speed picked up every second. Okay? Now, there's a change in direction, E. At what values does t, the particle, change direction? How do we find when the particle changes direction? When it goes from negative to positive or positive to negative, right? What's the only way, you know how number lines work? What do you have to pass through to go from negative to positive or positive to 0? So, we're actually looking at A, B, C, D, E. We are looking for, I'm just going to make a little more space here. E. Changes direction when V equals 0. I'm going to just write this down. That's your thought process. Okay? And actually, this is a basic idea that you're going to use throughout the calculus course when you're going from increasing to decreasing functions and stuff like this. You're looking where zeros happen. Anyways, I set the velocity function 0 is equal to 2t minus 3. So what I've done is I've subbed in 0 for velocity, right? And then it's pretty easy to solve, 3 halves. Yeah?
Will it do when distance is in or when velocity is in? Because it's a particle.
Changes distance when the velocity is 0. Because you must stop. Just think of throwing your eraser up in the air. It changed direction when it stopped, right? Went from positive direction to negative direction. Yeah?
But isn't this graph position as a function of time, so then how would you be able to graph velocity also on that?
Gotcha. How about this? We'll finish this and then we're going to maybe use a graphic calculator to come up with this, okay? And then some will be revealed. Maybe all will be revealed. F. Where's the particle when S is a minimum? Where's the particle when S is a minimum? F.
As distance is linear,
When the position is at a minimum.
we can do d
Where is, without a calculator though,
this side equals 1.
well, let's just think about this. Remember how I said right off the bat, at time equals 0, you're at 2, and then you end up at 12, right? Now, after 1 second, just plug in 1 into here. 1 squared minus 3 times 1 is what? Negative 2. Or sorry. 1 squared minus 3. It's at 0. So somehow it went over to here, right? So really this trip was, and then we know it actually goes a little further because it goes 1.5, right? Into the negative distance from whatever starting point you Now, this is what the position is
Can you
describing.
find the vertex?
So we had to find this spot where it was 0, right? Because the first few seconds it was going to the left. That's all that means, it was going to the left of its starting point. And that, the minimum distance,
Can you find the vertex?
is the vertex of that, yes? Or in other words, where the velocity was 0. Because it went to the left. It starts out at some position we call 2. It goes back. That's the minimum distance, and then it turns around and goes this way, right? And we know it's quadratic, so it's not going to change the angle.
Like minimum distance v0.
We know that the velocity is 0 at the minimum distance. We also know that the time is 3.5 seconds because we just solved that. Now, this one is a head scratcher, kind of, if you haven't thought about it as much. So the minimum, what we're looking for is the minimum position value. It'll be to the left of 2 anyways. And we know that it must have went left initially until 3.5 seconds elapsed, then it turned around and went to the right, just from what we figured out in E. So it should occur at 3.5 seconds. So we are finding S of, and I was making a nice S, 3.5. Now let's pretend this is a non-calculator section. So T squared, 9/4. Minus, what is it, 3T? Or, no,
Yeah, 3T.
yeah, it was 3T. Okay. Minus 3 times the time, 3 halves. Times 3 is 9 halves. What was the last one here? Plus 2. Now, I can already see, I'll write it down as plus 2 and do my arithmetic after. Okay. So out of 4 is the best way to work, right? 9/4 minus 18/4 plus 8/4. Then you can do your arithmetic just fine, right?
Negative 1 over.
-1/4?
Yeah.
Yeah. Yep, just double checking. And that is a position, so it's in meters. Negative 0.25 meters. That's the most extreme, it goes to the left. Now, tying this all into the graphs here, I'll just pause this.